If you haven't already, please print the handout. We're going to talk about gas laws. So these are just different laws that describe how gases behave. Before we get to that, let's talk about some standards and some terminology here. So we could talk about standard pressure and standard temperature. This is just ways that scientists communicate what the temperature and pressure is when they perform a certain experiment. So if you see the word standard pressure or standard temperature, it just means 1 atmosphere of pressure, which is 101.325 kilopascals. And the standard temperature just means 0 degrees Celsius. Or if you convert that to Kelvin, that would be 273.15 Kelvin. So one thing you should write down is how to change your temperature into Kelvin. The reason we need to do this is because when we start to perform calculations involving these relationships between pressure, volume, and temperature, we can't have negative values. So because the Celsius scale can involve negative temperatures, we need to convert it to a different temperature scale that does not have negative values. So that's where the Kelvin scale comes in. Basically, all you have to do is take whatever your temperature is in degrees Celsius and add 273.15. That's how you change to Kelvin. So we could talk about standard temperature and pressure. So standard temperature is 0 degrees Celsius, which is 273.15 Kelvin. Standard pressure, remember it's 1 atmosphere, which is 101.325 kilopascals. So this, if you see the experiment was conducted at STP, that just means standard temperature and pressure, 0 degrees Celsius, 101.325 kilopascals. But really, who wants to conduct an experiment at freezing temperatures? There's something else, standard ambient temperature and pressure, so SATP. This modifies the temperature to a more comfortable 25 degrees Celsius, and it changes the pressure to a nicer number, 100 kilopascals. It's just a nicer number to deal with when you're doing your math. So just so you are aware, when the question says STP or SATP, this is what they mean. They're telling you the temperature and pressure. So these gas laws are going to show you the relationships between pressure, volume, and temperature. We'll start with the relationship between pressure and volume. And to illustrate this, think about an air pump. What happens to the volume inside the cylinder as you push down on the plunger? Well, you can see here the volume gets smaller. So if you think about the gas particles inside the air pump, the volume that they're taking up decreases as the pressure increases. And the opposite relationship is true as well. If you decrease the pressure, the volume of the gas increases. This is called Boyle's law. And the law is P1V1 equals P2V2. This is similar to the dilution of solutions when you had C1V1 equals C2V2, except now we're talking, instead of concentration, we're talking about pressure of a gas. Now this relationship holds true only if you keep the temperature constant. Let's talk about the next relationship. So the relationship between temperature and volume. To illustrate this, think about a balloon. If you've ever seen a balloon get put in a freezer or left out in a vehicle or left out in the cold, it shrivels up. So as the temperature decreases, the volume of the gas decreases. And the opposite is true too. As you increase the temperature, the volume of the gas increases. This is Charles' law, and it states The relationship between volume and temperature is proportional. So if I compare in my initial conditions, and now I increase the temperature, that means I'm increasing the number on the bottom of my fraction. There's going to be a corresponding increase in the volume to keep the total value constant. So as I increase the temperature, the volume has to increase to compensate, and vice versa. And this relationship holds true when you keep the sample at a constant pressure. There is also a relationship between temperature and pressure. And to illustrate this point, think about a pressure cooker. If you've ever used a pressure cooker, the way it works is you put some water inside the bottom of the pot, you seal the lid, and you put it on the stove, or you plug it in if it's electric, and you heat up the water. And as you heat up the water vapor floating around inside the pot heats up, and it expands, and it moves faster and faster. And we know when particles move faster and faster, there's more collisions with the surface of the inside of the container, which builds up the pressure. So as you increase the temperature, the pressure increases as well. And this is called Gay-Lussac's law. And it states the relationship between pressure and temperature is proportional. As I increase the temperature, the bottom of my fraction, to keep the value constant, the pressure also has to increase. And of course, this holds true only when the volume is constant, like in a pressure cooker. So we now have 3 different laws that describe how gases behave, and we can combine all of those together into what's called the combined gas law. P1V1 over T1 equals P2V2 over T2. So the way you would use this is you're comparing initial conditions with final conditions. So if I start with a certain temperature and a certain pressure and a certain volume, and I make a change to the temperature or the pressure, let's say, well, now that change in temperature, that's the new temperature over here. When you change the pressure, that's the new pressure over here. So if I know the pressure, volume, and temperature at the beginning, and I know changes made to 2 of the other variables, I can calculate the missing one. So in this case, I could calculate the missing volume using some algebra. So if you flip to the next page, we'll go through an example of that. So I'm not going to go through all of these examples with you right now, just the first one. So a sample of helium gas is collected at room temperature in a 4.5 liter balloon at standard atmospheric pressure. So there's that word, standard pressure. The balloon is then submerged in a tub of water, also at room temperature, such that the external pressure is increased to 110.2 kilopascals. What will the final volume of the balloon become? So I'm going to start with my combined gas law, and now I need to fill in some values. So room temperature, it starts at room temperature, so that would be T1. What would be T2? Well, it says after it's submerged in the water, it's also at room temperature. So T1 and T2 are the same. We don't need to know what the temperature is because all we need to know is that there's no change. So T1 and T2 are the same. They're not changing. We can actually remove that from our formula here. So what we're left with is this. Let's keep looking for values. We have a 4.5 liter balloon. That's the initial volume. That's V1. We have a standard atmospheric pressure, so standard pressure, that would be P1, 101.325 kilopascals. the pressure is increased. So P2 is 110.2 kilopascals. So we know P2. We know P1, we know V1, we know P2, and we're asked, what will the final volume of the balloon become? Well, that's V2, so we're going to solve for V2. I rearrange my formula to solve for V2, and now it's just a matter of plugging in my numbers and solving. So you should get an answer of 4.13 liters. Let's skip down to the bottom of the page and talk about the relationship between volume and number of moles. Well, this one is kind of common sense. If you increase the number of moles of gas, that means you have more gas. It's going to take up more space. That means the volume will increase. If you decrease the amount of gas, the volume will decrease. It will take up less space. So Avogadro's law shows that the number of moles of a gas and its volume are proportional. Flip the page. So if you combine all of these ideas between pressure, volume, temperature, and number of moles, we arrive at the ideal gas law. So remember, an ideal gas is that hypothetical gas that is just a simplified model of how a gas behaves. If we combine all those laws together, we get PV equals nRT. The pressure times the volume equals the number of moles times this, which I'll get to in a minute, times the temperature. P is the pressure, V is the volume, N is the number of moles, T is the temperature, and R is something called the universal gas constant. These are the units that you need to use whenever you're plugging numbers into the ideal gas law. Now this universal gas constant has a value of 8.3145 for every gas, and its units are weird, to say the least. They're called kilopascal liters per mole Kelvin. So because these are the units used in the universal gas constant, you have to use the corresponding units for P, V, N, and T. Let's do an example. Dentists sometimes use laughing gas, which is just dinitrogen oxide, to keep patients relaxed during dental procedures. A cylinder of laughing gas holds a volume of 57.3 liters. The pressure is 108 kilopascals, and the temperature is 294 Kelvin. Now we are asked how many grams of laughing gas are in the cylinder. I'll start with my ideal gas law. And the question is asking me how many grams are there? Well, I don't have a mass in grams in this formula, but I do have number of moles. And I also have a way of changing moles into a mass. So I'm going to start by solving for number of moles. So I rearrange my formula, and then I plug in my values from the question. Now, I haven't been showing units in the calculation, but you have to make sure that you're using kilopascals, liters, and Kelvin for your pressure, volume, and temperature. If the temperature was given in Celsius, for example, I would have to change it into Kelvin before I plugged it into my equation. So I have 2.53 moles of this substance in my container. And now I go back to Unit 3 and figure out the mass using the moles and the molar mass. Remember, molar mass is for this compound here, so I have 2 nitrogens, 1 oxygen, which gives me 44.02 grams per mole. Do my math, and I get an answer of 111 grams of laughing gas. So there you have an idea of how you can use the combined gas law and the ideal gas law to solve different problems.